Assalamu alaikum. Welcome to another lecture on power electronics. In today's lecture, we will discuss about the three-phase inverter. Three-phase inverters are widely used in industry because most of the industrial applications are driven by three-phase machines. So a three-phase inverter has a lot of different varieties available in the literature. We will start with the very basic one, which is known as a six-step inverter. A six-step inverter is basically an offshoot of a square wave inverter, where we will turn on the switches in the same fashion as we did for the square wave inverter. However, we have three arms or three legs available. So we have a leg A for phase A, this is for phase B, and this is for phase C. So you can see here there are a total of 6 switches that constitutes a three-phase inverter. Each of the arm or each of the leg has a center point through which the load is actually connected. Remember that this load can be either a Y connected load or a delta connected load. So we can connect the load in either of the configurations. However, based on this configuration, we need to compute the currents and the voltage accordingly. In a square wave inverter, as you can see that these 6 switches are numbered such that we have this S1, this is S3, this is S5, this is S4, 6 and 2. The numbering scheme looks quite bizarre in the first sense, because this is 1, 3, 5 and here we should have 2, 4, 6, but it is 2, 4, 6 and 2. So these are numbered according to the turn on sequence. So we can see here that all these switches, when we turn on the switch, we first turn on the switch S1, after which we turn on the switch S2 and this S3, 4, 5 and 6. So each switch is labeled in the sequence at which we turn on by applying the gate pulse here. Moreover, all the switches have a switching action that takes place every T by 6 or 60 degree. So because this T is equal to 360 degrees, so this becomes equal to 60 degrees. So when we turn on the switch S1, we will turn on the switch S2 after the delay of this 60 degree, and thereafter we turn on the switch S2, we wait another 60 degree, and then we turn on this switch S3, and so on and so forth. The sequence of gating actually occur. So the instantaneous voltage between these points A, B and C, that is the VAB, which is between this point VAB and this point VBC and this point VCA, they depend entirely on what type of configuration we are actually using. So for a delta load, phase current can be calculated once we know what is the line to line voltage. However, for a Y connected load, the line to neutral voltage is actually required to find out the line or the phase current. So let us see how we can find these currents. So here is the switching scheme of a three-phase inverter. As you can see here, at time t is equal to 0, we turn on the switch S1, which essentially turn on for 180 degree, and that is why we call it a 180 degree conduction mode as well, because every switch in this 180 degree conduction mode conducts for complete 180 degree and then it actually turns off. This time period, if this is considered 0, then this S2 is turned on after this T by 6 or 60 degree delay, and thereafter after we turn on this switch S2, this time delay is also 60 degree. So in a nutshell, we can say that this S1 has a phase difference of 60 degree with this S2 and a phase difference of 120 degree with this S3. Notice that we have seen here, like every inverter for single phase that we have studied, we cannot turn on this switch S1 and S4 simultaneously. So S1 should be equal to the complement of this S4. So if this S1 is 1, then this S4 should be equal to 0. So they should have a complement here. That is why when this S1 turns off, even at that particular point, after turning off this S1, this S4 is actually turned on. Same goes for the switches S2 and S3 as well. So when this S2 is actually conducting, we do not have a conduction for this S5, which is the high side switch for phase B. Similarly, when we have this S3 conducting, which is the high side switch of phase C, then at that particular time the low side switch on phase C or leg C, it is equal to 0. So together we can make sure that whenever we have one high side switch turned on, then there is if with one high side switch on, there is a return path through two switches, such that let me show it here, such that when we have this S1 turned on, then we have S6 and S2, they should actually turn on. So the gating sequence is something like this, that we have 1 2 3, then 2 3 4, then we have 3 4 5, then we have 5 6 1, and then we have 6 1 and 2. So in this way the sequence of switching takes place. So you see here, when we have 1 and 3, they are turned on, then the return path is through this switch S2. When we have 2 and 4 for the return path, then this 3 is actually holding the total current which flows into the system. So this is how we will evaluate this whole scheme, and we should notice that sometime we have two top switches working with one bottom switch, and sometimes we have for the other time we have two bottom switches conducting with one high side switch conduction. So in here you can see that we have mod number 1. So for mod number 1, we say that this mod, so we say that for this mod 1, which is when we have omega t less than pi by 3, that is equal to 60 degree. So if I make the system for a Y connected load such that is shown here, then at that particular time we have, this is the VDC. So you see here from 0 to pi by 3 what switches are on. So let us go back here and see at this particular point, from this is the mod number 1, this is mod number 1. So we have switch S1 turned on, we have S5 turned on, as well as this S6 turned on. So if we move back here, so we can understand that this point A is connected with this VDC. So we have, let us say this point is A. Similarly, we have this 5 turned on, so we have this point C also turned on here, and apart with this S6 was also turned on. So let me say this is the point number B. Considering it a resistive load, just to have a better understanding here, so that we can apply the basic laws without having any difficulty, let us say this is R, this is the R, and this is also R. So now we have some current I1 that is flowing into this circuit. Looking into this particular example, that R equivalent for these three is equal to 3 by 2 R. So what is the value of this I1 here? This I1 is this VDC over R equivalent, that is equal to 2 by 3 times the VDC. So what is the value of VAN with respect to the neutral point? So VAN is equal to this I1 into R by 2, because the current is actually dividing between these two branches. So that becomes equal to VS over, or VDC over 3. Similarly, this is also true for VCN, and that is also equal to VDC by 3. However, for this VB is actually holding total amount of current here. So VB and N is equal to 2 by 3 minus 2 by 3 times the VDC. So you can see here for this mod 1, while we have this VA and VC having a voltage equal to 1/3 of the applied voltage, this VBN is having minus 2 by 3 of the VDC. So let us on the same time, let us draw some waveforms here as well, so that we can actually see it in a better way. Let us draw the first waveform, which is let us draw it with the red color. So this is the VA of n, and we have, let us say we have, this is the pi, this is 2 pi, this is 3 pi. So VA of n during the first time interval, which is this is pi by 3. So for this particular time, this VA of n is equal to VDC by 3. So this is the value of the VA of n during the first time interval. Similarly, let us draw the second waveform, which is the VB of n. VB of n is also equal to VDC by 3, and therefore it has this type of a shape. For the third waveform, that I should draw with some other color. For example, this blue color is okay. This is VC of n. VC of n is equal to minus 2 by 3 VDC. That is equal to, we have, for this particular time, we have, this is the VDC, this is the VCN. So this is for the mod number 1. Now on the similar grounds, we can compute the value for the second mod, which starts from pi by 3 to 2 pi by 3. So for mod number 2, that starts from pi by 3 is less than omega t is less than 2 is a less than equal to less than 2 pi by 3. So for this particular time, we have to see what is the switching sequence here. So let us move back here and let us see what happens in the next, which is this second mod. During this mod 2, we still have this S1 on. However, S5 is now turned off. So S1 is on, we have S2 on, and we have S6 on. So 1, 2 and 6 are the three switches which are contributing during this particular time instant. 1, 2 and 6, which means that now we have two bottom switches on, and we have only one top switch, or the high side switch, which is turned on. So the equivalent circuit that will suffice for this mod 2 is something like this. So we have this is point number B, because point B is what is having the switch number 6. Then we have this point C, which is the switch number 2, and then we have switch number A1 connected, so that constitutes for the phase A. So now we have a current, which is this I2. On the similar grounds, because the resistance is essentially the same, so but the value of this I2 is now equal to 2 by 3 R into VDC. So that is equal to the same exact expression. Using this expression, I2 is equal to 2 by 3 VDC over R, we can find out the value of VAN to be equals to Vs 2 by 3 into V of S. V is equal to I into R, and this is the value of the load available here. How about this VB of n? VB of n and VC of n will share the same voltage, because the current is dividing equally among these two loads. So we have equal to minus I2R over 2, that is equal to minus VDC over 3. So for this particular time instant, from this pi by 3, to this particular instant, which is 2 pi by 3, we have Va of n equal to 2 by 3 V of S. So this will rise to this particular point and will retain for this much period of time. However, during this particular time expression, the value of this VBN is equal to minus VDC by 3. So it will be shifted on the negative side, and it will retain its value till this particular time. Similarly, for this VCN was earlier at minus 2 by 3 VDC. However, it will have a value equals to minus VDC by 3. So you can see here that we have, for this particular time period, we have this type of a shape for this VCN. Now let us go for the mod number 3. For mod number 3, we again need to review the switching schemes before we draw the equivalent circuits. So for this mod number 3, which is for this one period of time, you can see here we still have switch S1 conducting. Also this S2 is also conducting, but at the same time we have now S3 comes in place. S4, S5 and S6, they are not contributing for this mod number 3. So we have 1, 2 and 3 that is we have now 2 high side switch and 1 low side switch conducting. So this switch is conducting, then we have this switch is conducting, this switch is conducting, and then we have this switch S3 conducting. So let us draw the equivalent circuit to proceed further. So for this mod number 3, we have again, this is from 2 pi by 3 is less than equal to omega t is less than equal to pi. So the expression here is same like the previous one. There are 2 resistances that will be connected with the positive rail, and 1 load which is connected directly to the negative rail. So now we have the current, which is this I3, and this I3 is equal to 2 by 3 VDC over R, and this is all R. So now because 2 top side switches are conducting, so this point will be A, this will be equal to C, and this will be equal to C, because 2 is connected with the arm number C, so this will be equal to B. So now we have this I3 equal to 2 by 3 VDC over R. So the value of VA of n, that is equal to VB of n, that is equal to I3 into half of the total resistance, and that is equal to Vs over 3. However, for this VCN, that is equal to minus 1 by 3 into R. So we have minus 2 by 3 into VDC. So if we draw this thing, we should notice that this VAN and VB of n, they should have a value equal to 1 by 3 of the VDC. So VAN and VBN, they should have a value equals to, this is VAN and VB of n, they will be having a value equals to VDC by 3. So let us draw. So VA of n will takes on the value equal to this VDC by 3. So we have actually made a little bit mistake here. So let us first correct this mistake. VCN at this particular point during the first time interval, VCN is equal to VDC by 3. So that is equal to something here. This is the VCN. During the second subinterval, this VCN is equal to minus VDC by 3. So it will come on the bottom side, and for this period it will become equal to minus VDC by 3. In the third subinterval, this VCN is equal to minus 2 by 3 VDC. So that will be equal to something like this one. For the period till this pi. For this VB of n, VB of n is equal to, during this mod 1, this VB of n, we have also made it wrong, so let us remove this one here. Okay, so this VB of n during this mod 1 was equal to minus 2 by 3 into VDC. So this is the VB of n, and for this mod number 2, this VB of n is equal to minus VDC by 3. So it will have a shape something like this for the second mod. And for the third mod, we have VCN equal to VBN equal to VDC by 3. So that is equal to VDC by 3 means that it will go up and it will retain this particular value from the time period between 2 pi by 3 till pi. Now you see here that in a nutshell, these phases will actually having the 6 steps as follows. So it will retain its value from this particular point till this particular point, and then we have this type of a shape for the waveforms. Similarly, for this red block here, it will come here to this from this time interval to this time interval, it will become equal to minus VDC, and then we have this type of a shape for the VA of n during the rest of the operation. Similarly, for this VC of n, it will go back to this VDC value, VDC by 3, and then it will move on to VDC by positive VDC by 3, and then 2 by 3 into VDC, and then it will have this type of a shape. So in a nutshell, if you see here, this VA of n, this VB of n, and this VC of n have values equals to 2 by 3 into VDC, or it will have a value equals to VDC by 3. So it has actually 6 steps, and that is why we call it a 6-step inverter. So if you see here, the first step is this one. Then we have this second step. This is the third step. This is the fourth. This is the fifth, and this is the sixth step. And therefore, it is known as a 6-step inverter with 180-degree conduction. Why we call it a 180-degree conduction? Because if we see here, each of the switch conducts for 180 degree, as it is evident from the timing diagram of the switch sequence. So every switch is actually contributing its conduction for 180 degree. So let us move ahead a little bit on this topic and develop, because these are the neutral waveform, we need to develop what is the phase voltage, that what is the shape of the phase voltage. So again, let me draw some lines here. So now if you see, I want to find out what is the VAB, VBC, and this VC of A. So for that, because I want to find out what is the voltages here, so let us say this is VAB, this is VBC, and this is VC of A. Now this VAB is equal to V of A minus V of B, and this is VB of n, and this is VA of n. So if you see here, during the 0 to pi by 3 interval, we have VA of n equal to VDC by 3, whereas we have VB of n equals to 2 by 3 into 2 by 3 times the VDC. So during the first time interval we have VA of n equals to VDC by 3 minus, with this sign negative as well, minus 2 by 3 into VDC. This becomes equal to the VDC. So we have a VDC available for this 0 to pi by 3. For this particular interval, VA of n is equal to 2 by 3 VDC. However, this VB of n is now equal to 1 by 3 into VDC. So again, essentially, it will have the same value equals to VDC. So this is equal to VDC. So now we have the VDC available for 2 by 3 pi of the positive half cycle. For this time interval number 3, we have VA of n equals to VDC by 3, and we also have VB of n equals to the same voltage VDC by 3, and now this is a positive side, so we will not see any voltage for this particular time interval. For this waveform, for the negative half cycle of this VA of n, we have minus VDC by 3 for this VA of n, and for this VB of n we have the 2 by 3 into the VDC. So if we sum up these two things, they will ultimately provide me again a value equals to VDC for this much amount of time. In here we have again these two values are equal in magnitude, and they have and therefore they will cancel each other. So we will again see this type of a waveform. So we have an output which toggles between VDC, minus VDC, and 0. So we have actually a 3-stage output available between the phases. For this VBC, we have again for this VBC we have VB of n minus VA of n. Now what is VC of n? What is this VB here? VB is minus 2 by 3, and VC is equal to plus 1 by 3 VDC. So that will become equal to the value it becomes equal to the minus of VDC, and this for this particular period of time only. From this pi by 3 to 2 pi by 3, this value is equal to 1 by 3 times VDC, and this VC of n is also equal to minus 1 by 3 into VDC. So what we will get here is we will get a 0 volt here, so there will be no voltage here, and after that we will again see a voltage. Using the same particular knowledge, we will develop this type of a voltage for the VBC. For this VC of A, we will develop the same knowledge here, as providing we are using the same logic here. We will see this kind of a voltage, and so on and so forth. So you can see here that we have a phase voltage which is having 3 different levels available at the output, and that is the phase to phase voltage has either a value equal to the plus VDC, or it has a 0 value, or it has a minus VDC value. However, the phase to neutral voltage VA of n, VB of n, and VC of n, they have different steps available, and there are 6 steps available in one complete cycle, and therefore owing to this property, this type of an inverter is known as a 6-step inverter. If we go further and we'd like to see what kind of voltage and the current relationship we will have, this is the same thing that we have discussed earlier. So if we go further for the Fourier analysis of the output value, where we have some fundamental frequency as well, the interesting point here is that the frequencies of harmonic appear at 6k plus minus 1, and for k is equal to 1, 2, and so on. So if we have k is equal to 1, then we will have this harmonics available at 5 and 7. If this k is equal to 2, then we have 12 minus 1 is equal to 11, and 12 plus 1 is equal to 13. So we have 5, 7, 11, 13, and without having any triple harmonics. So, and so is the even harmonics. So in this 6-step inverter, we have got rid of the, we have eliminated the triple harmonics, which are a multiple of 3, which means 3, 9, and so on and so forth. 3, 9, 15, 21. Every triple harmonic is now gone, and so is the even harmonics. Even harmonics do not exist. So the Vn line to line voltage is equal to is governed by this particular expression, as you can see on this particular graph, where the value of this n is only for the fundamental, the 5th, 7th, 11th, 13th, and so on and so forth. For this particular waveform where we have the current available, the current will have to pass through the switches, and as you can see here that there is a slight delay in the current owing to the inductive nature of the load. So we have, when we have a positive VFN supplied, then the current rises from this particular value to this particular point. Again, this depends that this curve depends on the ratio of the inductor resistance, and this same goes with this VFN. So we have a current shape which is more like look like a sinusoidal waveform owing to the inductive property. Well, for this three-phase inverter that we have studied so far, it actually has the same issues that we discussed for a quasi square wave inverter and for a square wave inverter. The foremost issue is not actually to get rid of the third or triple harmonics. The issue is to push the frequencies at a range which is a larger multiple of the fundamental frequency, so that the filter design is quite easy. But before, and for that, we of course we have studied this PWM, and that can be applied on a three-phase inverter as well. We will discuss this shortly, but before that we need to simulate, and we need to see are we capable of validating these results that we have obtained in this theory lecture. So let us first go for the simulation, and thereafter we will come back to the topic of the pulse width modulation based three-phase inverter. So I have developed a three-phase inverter with 6 switches that are named as Q1, Q3, Q5 on the connected on the high side, and Q4, Q6, and Q2 connected on the low side. To make the things more clear, I have made this VDC equal to 120 volts, so that we can visualize the line to ground voltage by 2 by 3 VDC and 1 by 3 VDC with more clarity. In addition to that, we have connected the ammeters to measure the load currents. The load is actually an RL series load with a resistance value equal to 10 ohm, and the inductance equals to 0.001 ohm, 0.001 millihenry. To measure the line to neutral voltage, we have connected these voltage probes here. This measures the VAN, this is for VB of N, and this is for VC of N. To measure the line to line voltage, we have connected another voltage probes here. So I can get the phase to phase voltage VAB, VBC, and VCA, and we will visualize that these three voltages are having only three voltage levels. That is, they can either be at positive VDC, that is equal to 120 volt, or it can be equal to 0 or the minus of the VDC. To measure the DC current that flows through this given circuit, I have connected an ammeter here. Let us simulate this particular circuit for a total time of 0.1 second. So now that the simulation is over, I have these variables available that can be plotted here. So let us plot VA of N. So you can see here that this VA of N is having three different steps during the positive half cycle and three different steps during the negative half cycle, and therefore what we actually studied in our theory, it is validating in the simulation as well. So if you see here the voltage here at this particular point, that is equal to 39, that is equal to 40 volts, which was that we were expecting to have 1 by 3 of the VDC available during the first step. The voltage here is 2 by 3 of VDC, and that is equal to 80 volts. and thereafter we again reach to 1 by 3 of the VDC, that is equal to 40 volts. The same is the case with the negative half cycle. You can see here this is minus of 40 and this is minus of 80, and thereafter it again reaches a value of minus of 40. The other two voltages, if we plot the VB of n here, then you can see that this VB of n is shifted in the same sequence as we studied in the theoretical analysis. If I plot the VC of n here, you can see here that all of these waveforms actually comply with the theoretical analysis we did before. As far as the line-to-line voltages are concerned, VA of B, if you can see here, this VA of B is toggling between 0 plus VDC, then again back to 0, and then to the minus of VDC, and that value is equal to 120 volts. So you can see here that for this VAB we are getting 120 volts at the output, and thereafter it goes to 0, and this is a time when we have VA and VB both equals to the same potential difference. So you can see here VA of n is equal to 40 volts, VB of n is equal to 40 volts, and consequently VA of B is equal to 0. Same goes for the other two phases, which are VC of A and the VB of C. The next thing that we need to find here is the fast Fourier transform to verify that the harmonics appear at an order of 6k plus minus 1, where k where k is equal to 1, 2, 3, and so on and so forth. This means that for the first harmonic that should appear in the output in the FFT spectrum, it should be at a k with k equal to 1. It should appear at the fifth multiple of the fundamental, and then the second will be at 6 of k plus 1, that becomes equal to 7, and thereafter we should visualize that the 11th, 13th, 17th, 19th, 23, 25th, all the harmonics should be present here. Note that in this type of an inverter system, there is no triplen harmonic in the output. So let us clear the screens and we uh, plot the fast Fourier transform. So this is the fast Fourier transform of the VA of n. Let us bring this to 2000, that can cater for frequencies up to 25. So this is the fundamental component here. So you can see here that the fundamental component has a frequency of 60 hertz, and that is what we set in here. If you see, all the gating blocks are set to generate a frequency of 60 hertz. So for the 60 hertz, which represents the fundamental frequency, the VA of n has an amplitude of 76.3 volt. Thereafter, we do not see the third harmonic here. So you can see this is 180 hertz here, and there is no spike here, which indicates that the third harmonic is absent here. Rather, we should see the next harmonic at the fifth multiple of the fundamental, and that is at 300 hertz. So you can see at this 300 hertz we are getting as a peak here with an amplitude equal to 15.2 volt. Thereafter we should see the seventh harmonic. The seventh harmonic is there, so you can see this seventh harmonic at 420 hertz do have some value, and thereafter we will not see any multiple of the third harmonic, that is there is no ninth harmonic. The next harmonic that appear here is the 11th harmonic at 660 hertz, and thereafter because this k is now equal to 2, the next harmonic should be at the 13th of the fundamental. So if I move in here, this is the 13th harmonic, which is a 780 hertz. So you can see here this is 780 hertz, and it has an amplitude of 5.8 volt. Thereafter, if we move ahead, so we have the 17th harmonic that should appear at 1020 hertz, and after the 17th we should see the 19th harmonic that is also present, that is at 1140 hertz. After this 19th harmonic, the next harmonic is available at 23rd of the multiple 23rd multiple of the fundamental frequency, and that is equal to 1380 hertz. So that's how we can actually visualize the the Fourier components present in a three-phase output that is generated as a result of this six-step operation. I encourage all of you to simulate the circuits that we study in this course. This will strengthen your grip on the professional softwares, as well as it gives you a visual insight of how the circuits actually work. So that will create more interest for this subject. Thank you very much.